Hello and welcome. In this video I'll cover organic mechanisms, the detailed process by which reactants are converted to products, and how we represent them. This video will therefore focus on the curly arrow formalism as a tool to describe how organic molecules react. As with the previous video, Chapter 19 of Chemistry Cubed will be useful to you. So here's a very simple statement which happens to be true. Non-redox reactions typically require a nucleophile and an electrophile. The nucleophile has high electron density, while the electrophile has low electron density, and the two are attracted to one another. We represent the movement of electrons between them using curly arrows. Curly arrows are one of the most important things in organic chemistry, as they tell us what the electrons are doing during the reaction. Chemistry is all about the electron. Nuclei are just big heavy things that influence what the electrons do. So here comes a curly arrow in action. In this case, the nucleophile has a lone pair and a negative charge, while the electrophile has an empty orbital and a positive charge. The curly arrow starts from the lone pair and moves to the electrophile. This is because the electrons start as the lone pair and they move into the empty orbital of the electrophile. This straight arrow now indicates that a reaction is taking place. In the product, the nucleophile is now not charged because electron density has moved away from it during the reaction. Likewise, the electrophile is also not charged because overall it has gained electron density. And the product of the reaction has a bond that did not exist before. This bond was created by the movement of electrons described by the curly arrow. Therefore, the electrons that formed the lone pair of the nucleophile must now be the ones that form the new bond. Curly arrows are essential for explaining organic mechanisms. Without mechanisms, we have no way of systematically understanding the process by which reactants are converted to products, which is the chemistry. Without a systematic understanding of chemistry, chemistry isn't much of a subject. And the curly arrow, therefore, is chemistry. Now, let's go into more detail. First up, the two types of curly arrow. If a curly arrow has a full head on it, like this one, then it represents the movement of an electron pair. On the other hand, if it only has half a head, like these, then it represents movement of a single electron. So, a bond can be formed either by movement of one electron pair, like this, or by the movement of two unpaired electrons, like this. We'll talk more about radical arrows, single-headed arrows, in the next video. For now, I want to go through some rules for full-headed arrows. First up, we can generate an incomplete octet using a curly arrow. An incomplete octet means that the atom has a vacant orbital, making it unstable and reactive. Here, the electrons in this carbon-bromine bond flow onto the bromine itself. That leaves the carbon atom with a positive charge because electrons have flowed away from it, and the bromine with a negative charge because electrons have flowed towards it. The electrons have flowed out of this bond, so that bond no longer exists. However, we can never force a second row element such as carbon, nitrogen or oxygen to exceed its octet. A full octet means that all available orbitals are filled. There is nowhere to put any more electrons, so no extra electrons can be accommodated without breaking a bond. So this is not possible, as moving one of these lone pairs from the bromine into the bond would increase the electron density in the bond, raising it from single here to double here. That would make the carbon atom pentavalent, which cannot occur. Likewise, a curly arrow cannot make hydrogen exceed one electron pair. Next up, direction. curly arrows always move from negative to positive, never from positive to negative. A positive charge means the area is electron deficient, so electrons will not move away from it. Therefore, this curly arrow is incorrect. However, to correct it, all we have to do is turn it round. This one is fine, as it shows electrons flowing from the negative area to the positive area, which is what electrons do. Similarly, curly arrows never diverge from one another. So in this case, you would not get one curly arrow going to this bromine at the same time as another curly arrow goes to that bromine, because that would generate two bromide anions. The electrons flow towards that bromine and towards that one, and it would generate a double positive charge on this carbon. One positive charge on carbon is bad, two just is not going to happen in organic chemistry. Similarly, electrons will not move towards an electron-rich negative charge due to charge-charge repulsion. So, a curly arrow will never head towards a negative charge, and two curly arrows will never head towards one another. Note, however, that this does not apply for unpaired electrons and half-headed arrows, which are keen to get paired up, as shown on slide 5. Overall, then, curly arrows flow. Electrons travel in the same direction. Here we have a nucleophile with its negative charge attacking an electrophile with its partial positive charge on this carbon atom. The flow of electrons from this oxygen to this carbon would make a new oxygen-carbon bond. In order for this to occur, one of the existing bonds to this carbon must break to avoid it becoming pentavalent. Therefore, the electrons in this bond flow out onto the bromine. Overall, then, the electrons flow continuously this way from the place that they start to a place where they are happy to end up. Finally, you must always preserve the appropriate charge balance. Here, we go from a negative and a positive charge, and we create a product which has no charge, which balances. Electrons flow away from X, so it becomes less negative, and towards Y, which becomes less positive. Here, you have the opposite situation. We start with no charge, and we end up with a negative charge and a positive charge, again, which balances. Finally, we have this situation where we have a neutral molecule plus a negative ion, giving a net negative charge. In the products, we must therefore also have a net negative charge, this time on this species. Overall, then, we've discussed the curly arrow and how it shows the flow of electrons in an organic reaction, and I've gone through the major rules that govern full-headed curly arrows. Ultimately, as the curly arrow represents the underlying chemistry going on in a reaction, then if you fully understand how to use a curly arrow, then chances are that you understand chemistry. So it's worth practicing the curly arrow until you're confident with it. Over the next few videos, we'll practice lots of curly arrows.